Let's see what the rest of the windows look like here. Well, I see an open sign. Why don't we just see if we go on in and see what's happening. Hello, you folks seem to be interested in what's in this shop here. It's an electromagnetic experimental shop. If you want to come on in, I'll show you a lot more. Well, there's a lot of interesting things over on this table here that you're looking at, but the real story is told in the other part of this area when we show how energy transfers itself. But we'll get back to this after a little while, but why don't we start at the beginning? That's usually a good place to start something. But you folks want to pull up a chair over here, we'll go ahead and show you what we're really doing. Okay, folks. Just pull up a chair and sit down, make yourself comfortable. Can everybody see this here board? This is a Carrom board, and what we're going to be discussing right now is transfer of energy. But energy transfers itself in many different ways, and one way is that by bumping of mass to mass, or particle to particle, atom to atom, whatever. And so I want to show you how when things transfer energy by bumping, it transfers straight forward. But these are little circles, and most everything in nature is little orbs. So being on a flat plane, I can divide up this energy. If I hit this here off to one side a little bit, it'll send it off one way or the other. So energy can be divided up into many, many parts. And let's see if I can hit this dead center to show you how energy transfers itself. But this has no energy in it now, and neither does this one. I'm going to apply this energy with my finger. And this is called a shooter. And this is a Carrom board. I don't know if you ever played Carrom when you were a kid, but we did. And it's kind of like an indoor pool table. You play on the kitchen table. Now, I say this has no energy in it, but related to the Earth, it has no energy. Related to the sun is just traveling very, very fast. In fact, the matter is you and I and all of us have to travel over 1,600,000 miles in the next 24 hours to make it around the sun in that orbit that we have that takes us a year to go around. So it's relative to the sun, this has a lot of energy, but relative to the Earth, it's just standing still. So I'm going to apply energy to it and see if I hit this dead center and see how much it transfers this energy. That's pretty good. It pretty well stopped there. It went off to the side a little bit. You understand what I'm driving at here, so I'm just going to move along because I don't want to spend all the time shooting Carroms here. I want to show you how energy will transfer itself if you can confine molecules in a tube. The sound will transfer itself very readily and very efficiently. In fact, you can talk a long ways through a tube, and you don't have to talk loud. You talk normal voice, and they could carry maybe 200 or 300 feet in that tube, as long as it doesn't get out. If it gets out the end of the tube, and you have all these little orbs out here, it's going to spread sideways, and so it's going to get thinner. And but it doesn't only spread sideways, it spreads up and down because these little molecules, like of air, are little orbs. And so any energy leaving a point source, like it does at the end of this here tube, will spread not by the simple distance, but by the square of the distance, because it's spreading in all directions. And that's where the inverse square law comes into effect. But we're going to keep these molecules in the tube here, and I'll show you how fast they travel from one end to the other. It seems almost instantaneous, but it's not quite. In fact, I don't find anything that's totally instantaneous in any of these travels. Even light at 186,000 miles a second is instantaneous. So watch this here, Carrom, now. It just seems very rapid. I'll hit that one more time, maybe get a little bit better observation of it. Now, I'm going to do something rather interesting here. I'm going to take two Carroms like that. Now they say that many people will think that, well, let me show you the results first, and then we'll go into that part of it. So I got two Carroms. I'm going to hit this line of Carroms. You notice two Carroms go. If I took three, three would go. If I took four, four would go. Let me take three and show you. Don't have as much room down here to do this, but I'll do it. Didn't hit it very hard. The brake is coming right there. I'll try that again. You notice where the brake is, there's three of them are traveling. Many people will think if you had two Carroms, two go because of the double the weight. But that's not the answer to it. And so I want to prove that it's not double the weight that causes that. And the way I'm going to do that is I'm going to take a magnet. This magnet weighs 2.5 times as heavy as the Carroms. In other words, equal to 2.5 Carroms. And I'm going to hit this line of Carroms with this magnet. And you'll see a difference. You notice they're spaced out. They'll always be spaced out. One will take the most of the hit, and the second one goes some, and the third one. But they're always spaced out. Now, to prove always, I better hit it at least twice to show you that it always does that. You notice they're spaced out again. This one hit the wall and come back. It was over like that and come back. So what's taking place there is that there's two pulses going through. The two Carroms are so close together to start with, like that, they're right tightly together, that the pulses are following each other so close that the two Carroms are still close together at the far end, like that. It drives them off. Now, the exaggeration sometimes shows things up even plainer. And so let's take 6 Carroms as shooters, and let's have 4 of them here, and we hit it and see what takes place in a case like that. Now I'm using all these as the shooters. And again, I'm applying this energy with my finger. These have no energy in them until I drive them with my finger. And so let's see what takes place here. You notice 6 of them went and 4 stayed back. Just reverse the numbers. What seems to be taking place there is that the first 4 Carroms that hit drove all 4 Carroms, and the next 2 had nothing to hit against, so they just followed. Now if we push these all the way up against the wall here, we can demonstrate what echoes are all about. But before I go into that, I want to talk a little bit here about the frequencies going through the air. If I was talking and you were listening, the molecules go from my voice to the molecules don't travel, but the energy employs molecules that are up against your eardrum, and they cause a vibration of your eardrum, so you can hear what I'm saying. The denser a medium is, the faster sound travels. So whales can talk a lot faster in water than we can in air, because air is rather thin. But it all travels the same way. So the denser the medium, the faster sound will travel. Now if I pull these apart a little bit, I can show you I'll be making them less dense. Sound travels at about 1,100 feet a second, or 700 miles an hour. So it's moving pretty fast. No comparison, however, with the speed of light, which is 186,000 miles a second. If we had a big boom here in Fort Bragg, California, and San Francisco is around 100 miles airline from here. It would take only 8 minutes for that sound to go from Fort Bragg to San Francisco. So it's doing pretty fast. The sound where airplanes fly in that sound barrier, they're flying right at the speed of sound, and so they get a lot of vibration because they're flying right in that vibratory situation. But looking at the two pulses going through there, think of the number of pulses that are going up against your eardrum if somebody was playing a violin. And there'd just be a multitude of pulses using those molecules to transfer that energy from the violin to your eardrums. So let's go on to this here a little bit. I'll show you what takes place when I separate these. What I've done is made a thinner medium. We've still got the molecules confined in the tube. So if I hit this line of molecules, Carroms, you can see the flow of the energy going up and coming back. And so let's watch for that energy flow as the Carroms move from one Carrom hits the next, the next, the next, the next, the next, and hit the wall and come back. You see that flow of energy up and back, and the shooter comes back. When I had these all up against the wall, I should have shown you an echo, and I'll go back to that in just a minute. But let me show you one more time on this here. You'll notice that this here shooter goes up and stops right here. And the energy flows forward and then hits the wall and comes back and drives the shooter back. And so at this time, look at the shooter, see if you can recognize that pause that it takes before that energy comes back. It's quite obvious, quite apparent. Now, for many years, scientists have wondered, is energy a wave or a particle? Well, from my observations, I say energy is neither one. I apply the energy to the shooter with my finger. That shooter hits the next one, the next Carrom, and then when it comes back. So what's really taking place is that energy is employing the particle, and when the particle moves, it creates the wave action. But neither the wave or the particle is the energy. The energy is a separate force or influence that is applied to the shooter. Anyway, I think it'll be a long time before they ever figure out is energy a wave or a particle until they first recognize that energy is a separate force. Now, it's been advocated in the past that energy was totally contained in motion, and that's what energy shows me. It's contained in motion. Let me push these up against the wall. I want to show you how echoes come back here. I usually do that before I get into the whether energy is a wave or a particle, but let's show you here. Now I'm going to hit this Carrom. The energy go right up. These are all tight together now. Like if you're talking against a wall or someplace, and you get an echo back. So I'm going to hit this and we'll see if it comes back through. You notice the energy went up and come back, and it drove the shooter back. Well, somebody, I forget now who it was, sitting in the chair there, but I appreciate people like this. He says, "Come on, Larry." He says, "These are all tight together. They're simply bouncing off the end Carrom." Okay? That's a reasonable thought, at least, but it's not the way I see it. So in order to prove that, I pull this one Carrom back at the end, and I'll hit it. Now, if that Carrom moves, you recognize that the energy is going all the way up and all the way back. So let's see. If you can recognize that this end Carrom over here moving, and the shooter will come back. I saw it move. I don't know if you did, but anyway, that Carrom did move. It did go all the way and come back. So that shows that energy can employ a path going one way and come right back on that same path. No problem with that at all. Electrical current will do the same thing. It can reflect back on a path. Now, I mentioned earlier, if I pull this back and this energy spreads out from the point source here, it's going to spread in two directions. So that surface there isn't what causes the direction of the molecules to go a certain way. What I'm going to say is that the energy is employing a whole field of those molecules. And so the energy then, audio energy, bounces in relationship to the field, that spherical field actually, off of the hills or the walls or whatnot. See, here's a field of molecules. It's a rubber ball. It's kind of a plastic, flexible ball anyway. And I know it's composed of a whole bunch of molecules. But it doesn't bounce in relationship to the individual molecules and the roughness of the surface. It bounces in relationship to the collection of molecules. If I drop it like that, it'll bounce in relationship to the ball rather than the individual molecules. If you go down to San Francisco, to the Exploratorium, you'll see a big parabola, which is a parabolic dish on one side of the hall. Opposite side of the hall is another parabola, parabolic dish. It's made of concrete. If you talk in the focal point of this one parabolic dish, and the sound will go right across the Exploratorium hall there and come to the focal point of this other dish. Now, those dishes are made out of concrete. They're not very smooth. So it doesn't require a mirror or a better than a mirror finish to reflect sound, even if the sound is employing the molecules. It's a collection of molecules. In other words, it's a field of influence. It's employing a whole field of molecules. How would you describe a field? That's not an easy one. But if you took a gust of wind and see it blowing in the grass, the grass waves. But its energy is employing the wind to move a lot of this grass, but it's the size of that gust of wind that we're concerned with, not the individual blades of grass. So that kind of gives you some things to think about. And I think one of the main things I was referring to here was the fact that energy is neither a wave or a particle, but is a field of influence. Now, there's one thing I want to show you here. A fellow showed me the other day. I had this apart, and I was sending energy through this line of Carroms. And he says, what would happen, he says, if I took one Carrom out of this lineup? I'm going to hit that again and show you just going through. I've spread them apart now so you can see the flow of this energy. Now, it did a little harder than intended. Now what he said was, let me take out Carrom right about here. He took this Carrom out. Now what's going to happen? He says, now we get a space. That's going to happen. So let's just find out what's going to happen. You notice that Carrom went across that space, stopped there. When the energy comes back, it drove it back. It's back where it was to begin with. It just, energy went right across that space. I mean, the Carrom carried it right across. I'll show you one more time. You watching that space right there now? Just watch that. So I could spread these all out then, and the energy still go up and back, except that the further the Carroms have to travel, the more friction you have on the board. So this is the way audio transfers. Now, electrical current travels pretty much the same way, except that electrons repel electrons. And so I'll go to another experimentation in a short while and show you how that actually operates.